So this diagram is actually called Voronoi diagram. So this one will actually tell you this area represents the area of people who go to this specific Starbucks coffee shop, and this area represents the people who go to this one. This area represents the people who go to this one. In computational geometry, you will learn how to compute these areas specifically. So this is one application of computational geometry. The other one is rendering 3D models for molecules. So this is a caffeine molecule. You can do this sort of stuff also requires computational geometry. And the other one is geographic information systems. This actually is used to analyze the geographic data, because all the data you get is generally in you get a lot of data about a specific place. Let's say, for example, you take a forest. So for a forest, you know how much is the vegetation density at a place, or etc. Various sort of stuff. I mean, like if you want to know about a specific plant, you know how much a specific plant grows at some place or stuff. So computational geometry is also used in geographic information systems. It is also used in solid modeling. So if you want to create a model, etc., you need to use this. And another important application which you guys will most probably be interested in if you are interested in robotics is, yeah, robotics also uses computational geometry, because basically you will need to know how to program your mechanical arms or etc. to move. So you'll need to know some computational geometry algorithms for that. And then the other important application is computer vision. So computer vision, you basically get the details about for computer vision. Basically, you get the RGB values for a specific area. From that, you need to write algorithms to interpret that data. That also utilizes some computational geometry algorithms. All right. So these are some very basic some applications of computational geometry. So you guys know what a polygon is, right? Polygon, I guess you guys know it. And convex polygon is a polygon where all the angles are convex and not reflex. So all the angles are less than 180 degrees. Okay. So the third one is triangulation of a polygon. So let me show you what a triangulation is. Just a second. Okay, so this is triangulation of a polygon. So the whole thing is a polygon, and you need to divide it into triangles by drawing diagonals. Okay, so that's called triangulation. It is actually very useful in some other applications. So triangulation of a polygon, we'll be discussing that too. So you guys can stop me if you have any question anywhere. Yeah.
What was the name of that area, like the Starbucks one?
This one, this diagram name.
Yeah, that I.
Okay, that is called. Let me write it in the chat. If you are interested, you can look it up. It is actually quite complex. Thanks. I guess so. Yeah, it would be better if you know some algorithms. It would help you a lot if you want to do that. Okay, so you guys know what a polygon is, what a convex polygon is, and what a triangulation of a polygon is. Triangulation is basically dividing the polygon into triangles by drawing diagonals. Okay. So let's start with what a convex set is. In geometry, a subset of a Euclidean space is convex if given any 2 points. The subset contains the whole line segment that joins them. So let's consider these 2 points P and Q, and let's say this whole shaded thing is the set we are considering. Now, if you choose some points P and Q inside the set and join them, if the whole line is contained in the set, then that set is called convex. Now, this is a convex set, the left one. Look at the right one. You choose some 2 random points in the set. Let's say they are P and Q, and you join them. Now, some part of the line is not inside the set. So this set is not a convex set. So you guys understood, right? What a convex and not convex set is?
Yes.
Yeah. Cool. So If you have any question, you can ask, fine. And this is simple anyways. So now we'll be going to what a convex hull is. Okay, convex hull is generally defined for a given set of points. So let's say you have some n points you have. Now, what a convex hull of that set of points is, it is the smallest convex set that contains all the points. Let me show you an example. So these are the points. Let's say these are the points. These are the points you have, and convex hull of that set is, it is a set. It is a convex set. We discussed what a convex set is before. It is a convex set that contains all the points. So you can clearly see that the polygon, this is a polygon. This is the polygon. So you can consider the whole region inside the polygon to be a convex set, because yeah, it is pretty obvious why it is a convex set. So the convex set inside the polygon we drew, that is a convex. That is a convex hull containing all these points. So generally by convex hull, we generally mean the boundary of the convex hull, because that is the thing we'll be working the most on anyways. So for this set of points, we can see that this polygon is the convex hull. It's pretty clear why it is, because it contains all the points, and it is the smallest, because if you, let's say, if you rotate this edge into the inside the in this direction, in clockwise direction, you can clearly see that we will be missing a vertex. We will be missing a point. So yeah, this is the smallest one. And what do we mean by smallest? Because in general, whenever we talk about, we can generally talk about either the area of that or the perimeter of that. So what do you guys think it is? So what do we mean by the smallest convex set? Do you mean the smallest set with the, do you mean the set with the smallest perimeter, or do you mean the set with the smallest area? What do you guys think? Any guesses?
I think it will be area.
You think it'll be area? Okay, why do you think that?
Yeah, because we are trying to minimize the region that it is containing. Like
Okay.
the set is the
Yeah.
region all.
Yeah, it is intuitive to think that it minimizes the area, but actually what is the, I mean, by smallest we actually we can prove that it is the minimum in area and perimeter. I won't be going into the details of the proof. So yeah, you can just take this as an interesting fact. A convex hull generally is the set with the minimum area and the perimeter. Okay. So generally, if you have a set of points, okay, what we'll be doing now is, I will be giving you a flavor of the kind of algorithms, the kind of stuff we'll be doing in computational geometry. This is a very basic algorithm you guys will be learning if you take computational geometry. It is a way to compute convex hull. Okay, so let's say generally, let's forget about computer for a while. Let's say you have on the ground a set of pins, and you want to compute the convex hull of that. You can do this. You can take a huge rubber band, stretch it until it encompasses all the points, and then leave it. So if you stretch it something like this, the black one, and then leave it, it will ultimately end up becoming something like this. Now this blue boundary will be the convex hull of the whole set of points. So this, yeah. Okay, just a second. Sorry. So this is a physical way of seeing, physical way of, let's say, computing convex hull. So let's look at how we do it. Let's look at an algorithm or to how to compute convex hull. Do you guys know what an algorithm is? I mean, just an idea of what
Yes.
an algorithm is. Yeah.
Yes, it is a step-by-step process to solve any problem,
Yeah,
to
exactly.
reach to the solution.
Cool. Yeah. So okay, so we'll be looking at a basic algorithm to compute convex hull. Before I start, this algorithm is actually not that efficient. It is a very naive algorithm which takes a lot of time, and there are a lot better algorithms to compute convex hull. We won't be going into that because it won't be that simple to to explain that algorithm for you guys right now. You can actually look it up if you want, algorithm for convex. There are lots of algorithms for that. Okay, so let S be a set of endpoints on the plane. These are the endpoints you have. And okay, a point P, let's say a point P is an extreme point if there exists a line L of P through P such that all the remaining points strictly lie on one side of the line. So let's take this point. Now, whatever line you draw, it will have points on both sides. Like let's say if you draw a line like this, some points are on the left, some points are on the right. If you draw a line like this, some points are on the left, some points are on the right. So one thing you can observe about convex hull is, let's say this convex hull. Let's choose this point. Now, if you draw something like a tangent to the convex hull at this point, you can see that all the points lie on one side of the convex hull, right? It is intuitive. It is easy to see that all the points should lie on one side of the line. So what we know is, okay, so we will call such points extreme points. There should be one such line. Like if you draw some line like this, if you draw some line vertically, then all the points won't be on the same side. You should have at least one line. If there should exist at least one line such that all the points are on the same side of that line, and that line should pass through that point P. So we will call such points to be extreme points. Now you guys see why extreme points are always on the convex hull, right? Or uh, at least every point on the convex hull should be an extreme point. That should be easy to see, right?
Yes, yes.
Yeah. So this will be our main. This will be how we proceed to compute the convex hull. So a point P is an extreme point if there exists a line L through P such that all the remaining points strictly lie on one side of the line. And again, an extreme line passes through 2 points such that the remaining points lie on one side. So each edge, okay, so an extreme line actually passes through 2 points of the point set, and all the remaining points lie on one side. So here again, you can see that every side of the convex hull is actually an extreme line. It's similar to the point analogy. So okay, so extreme line, we have an extreme point and extreme line. And these are some basic definitions for this. The point Q is an interior point if any line through Q splits the point set. So if you draw any line, I mean like some random line, you can choose your line. For any such line, the line should split the point set. So there should be some points on the left, some points on the right. So this point Q is an interior point because you can imagine any line and some points will be on the left, some points will be on the right. Now this point is clearly not an interior point because you can draw a line like this and all the points are on one side. So this is an extreme point. And this blue line is an extreme line. You guys can see why, because all the points are on one side. And a point P is a boundary point if it is not an extreme or an interior point. This kind of points we generally don't consider because these things are special cases and we prefer to generally handle them separately. So generally in any computational geometry problem or any situation, we assume that the points are in general position. So what do we mean by general position is that no three points are collinear, and if there are some lines, we also assume that no three lines are concurrent or something. I mean, that's the general assumption to make our lives easier. I mean, I'm just talking about computational geometry in general because, yeah. And if there are such points such that 3 points are collinear or three lines are concurrent, we generally handle such cases separately because there won't be that many. And if there are that many, such an occasion would be pretty rare in normal algorithms and stuff. So yeah, so this is a boundary. A boundary point is one which is not an extreme or an interior point because. So let's take this line, this blue line. Now, if you draw that line through B, then it is not clear whether all the points lie on the same side or not. So yeah, boundary point is generally, you can think of boundary point as a point which is on the convex hull but is not part of the convex hull. So let's say in this example, if you have some point here, some point here, that point would be a boundary point. Okay. Now the vertices of convex hull comprises only the extreme points of S. edges coincide with the extreme lines only. So this is also easy to see, because if some other point is on the convex hull, let's say for instance, let's say some other point is on the convex hull, is on the convex hull as a vertex, then we clearly saw that such a point should be an extreme point. So yeah, convex hull comprises of only extreme points, and the edges of that are extreme lines. Yeah. So okay, let us be a set of endpoints in plane. Yeah. Now this is an extreme point. Okay, fine. The algorithm, what we do is, let's say for each point, what you do is, okay, we can do this for every two, choose some random 2 points. Now from now, if you now draw a line through those 2 points, now you check whether all the points are on the same side or not. Now, if all the points are on the same side, you add this line to the, let's say you have a set where you store the edges of the convex hull. You can add these 2 points, this line segment to the edges of the convex hull. So that way you can find out whether a specific edge belongs to convex hull or not. See, because you can actually check whether all the points are on the same side or not. Like, let's say this. Okay, I can't write, I guess. Just a minute. Okay, let's say this point is A, this point is B. Now, if you choose to check whether this line segment AB is an edge in the convex hull or not, what you do is, for each other point, you check. Let me say this is a line, this is a ray. You can check the angle, like you can check the angle. You can check this angle. You can check this angle. You can check this angle. Once you, if let's say some other point is, oh sorry. Okay. You say, let's say some other point is here, then the angle will be it will be something like this whole angle. You see, right? So it won't be that difficult to check whether all the points are on the same side or not, because you can see whether all the angles are less than 180 or all the angles are more than 180. And if there are some points which are at an angle less than 180 and some other points which are angle at more than 180, then you can conclude that this line segment AB doesn't belong to convex hull. Are there any questions here? This is basically just seeing how a line segment belongs to convex hull or not. Are there any questions? No? You guys understood this, right? It should be easy to check whether all the points are on the same side. So you can easily check whether the line segment belongs to a convex hull. Once you get all the line segments, it should be pretty easy, because you know which once you get line segments, you know which points belong to the convex hull, and then you can reconstruct convex hull from there. It should be pretty simple. So if you guys know complexity, it should be order of can anybody take a guess? I mean, if anybody of you know complexity, time complexity of this algorithm. Does anybody of you know what time complexity is? I guess you should know, some of you at least. Nobody? Well, okay. It should be order of n cube. N cube, because, okay, let's, order of n cube means the computer generally takes n cube number of instructions on average, let's say. So basically, because you have to check every line, that should be nc2, which is n square. I mean, like, this should be n into n minus 1 by 2. And then for each line, you should check whether all the other points are on the same side or not. So for each line, you will be doing n more computations. So it should be order of n cube. In case anybody knows something about time complexity, you guys can understand why it is n cube. So this is actually a very inefficient algorithm, because it takes very long time, because you need to check for every line, and then you need to check whether for each line you need to check whether each point is on the same side or not. It is quite inefficient. And there are let's say, I mean, like, if you if you say this is order of n cube time, so like if you give something like 100 points, let's say it takes something like time proportional to just a minute. Time proportional to 100 power 3, which is 10 power 6. There are much more efficient algorithms which take which take around order of n log n time. So yeah, if anybody of you are interested about how else you can compute convex hull and how can it be so much more efficient than the algorithm I described here, you guys can look it up. I think to understand that you just need some very basic algorithms knowledge like sorting and stuff. So if you are interested, you can always take a look. So you just compute the algorithm I said just computes the extreme lines and then creates a convex hull. Convex hull polygon whose vertices are extreme points. Yeah. Okay, so why are we talking about convex hull? So what's so special about convex hull? It's just a set that contains all the points and it is the small edge. So what's the big deal? Okay, convex hull is actually used it is actually a very important part of computational geometry because it is very useful. So let's take this example of biomedical applications. So what happens is if you want to map out how your lung is, like the shape of your lung or something, what we'll do is we'll have a patient inhale some fluorescent molecules which emit a certain type of radiation, I guess. You'll ask the patient to inhale that. Now they'll be releasing some radiations. From that you can capture like positions of molecules. So what you'll be having ultimately is some points inside the lung. Since let's say you tell the patient to inhale it deeply, so let's say the fluorescent molecules are in every part of the lung. So for every you'll have the radiation emitting from every part of the lung. So you'll have a set of points which are inside the lung, so which almost comprise the entire lung. So if you compute the convex hull of the set of points you get of the location of molecules, if you compute the convex hull of the location of the molecules, you will get a rough shape of how your lung is. So this can be used to map out the shape of your lung, and I don't know how this is useful, but I guess they'll look for some deformities in the lung shape or something. So this is one application. Patients are asked to inhale gaseous nanopods. Okay, fluorescent sensors provide their 3D coordinates via imaging, compute 3D convex hull. So what we just described above is for a 2D convex hull. 2D the examples we did. This is all in 2D space. We can do the same for 3D also. It will be the same. The definition will be the same. The set of points, the convex set definition will be the same, and the definition of convex hull will also be the same, except that the convex hull will be 3D now. So yeah, volume of hull is proportional to lung size. Okay, probably they will look at the volume of lung, I guess. Yeah. And another use case. So let's say you are doing let's say you have a very weird room or very weird path. You need to move your sofa from start to end. So if you don't want to actually test it out, but rather simulate it in your computer, you want to see whether you can move the sofa from here to there. So what it will be actually easier to compute whether a convex polygon, let's say a square maybe, a square can be moved from start to end. It will be easier algorithmically because it has all the curved edges and all the weird shape. So what you can do is you can compute convex hull of the shape, convex hull of the sofa, let's say, and you can test whether that you can move that from the start to end. Because this thing is useful because it is easier to test whether you can move a convex shape from start to end. It is easier to code actually. So yeah, this is also another application of convex hull. If the convex hull of the sofa avoids collision with the obstacles, so does the sofa. Okay, robot moving. So this is not just for sofa. Let's say you have an obstacle course and you want your newly designed let's say some bot which has eyes and stuff to move through that obstacle course. This one actually also is also implemented using convex hull. I think the robot will assume itself to be a will take the convex hull of itself. It will assume it to be a 3D 3D. It will assume itself to be a 3D, let's say, polyhedron, convex polyhedron, and then see whether it will collide with something or not. And since the convex hull generally encompasses the whole object, if the convex hull doesn't collide with something, the object will also not collide. So it is sufficient to check whether the convex hull collides or not. Okay. Not only the above mentioned applications, convex hull is also used as a sort of pre-processing in many other computational geometry algorithms. So let's say you have a problem and you want to design an algorithm for that. What you generally do is, before you approach the problem, if you know the convex hull of the data of the points you have, as I mean, like for a problem you have an input and you want to compute something for those points. So instead of directly going on with the algorithm, sometimes computing the convex hull and looking at the convex hull can give us more insights on how to approach, or sometimes just doing the convex hull will solve some part of the problem or something. So convex hull is actually very useful. Okay, so do you guys have anything to add, or do you guys have any questions until now? Otherwise, we can move on to triangulation. Triangulation is also a very important part of computational geometry. So yeah, do you guys
So
have anything to add?
I want to ask a thing question.
Okay.
So in 3D convex hull, we have to check the plane. Uh, we have to draw a plane and check whether all the points lies on the same side or not.
Yeah,
Like,
that thing you can do. Yeah, exactly. But the complexity will be much worse because you need to check for n cube number of planes because it should be nc3, right? So it will
yes.
actually, yeah, I don't know if there are any efficient algorithms for 3D thing, because let's say you actually send these nanobots and there will probably be millions of nanobots. So yeah, for millions of stuff you'll probably need a better convex hull algorithm. Yeah, so you can do that generally. I mean, the same
Yeah,
algorithm we discussed
I'm
for
talking about
2D
just
applies here.
basic one. Yeah.
Yeah, the same algorithm applies here too. Yeah, cool. That's a good observation. And yeah, anything else? Anybody else, or you, if you have anything else to add? Okay, then. So let's go to triangulation. Triangulation, I already said before, it is splitting a triangle into splitting a polygon into triangles using diagonals. So you guys know what a diagonal is, right? So let me show you a polygon. Okay, let's take this polygon itself. This is a polygon, right? This is the polygon. So let's diagonal is generally a line joining two vertices. Is this a diagonal? Is this a diagonal of the polygon? This is the vertex. This is the vertex. This is the diagonal.
I think not.
Yeah, no. Diagonal should actually all the points on the diagonal should be inside the polygon for any polygon. So let me draw another diagonal. Let's say this is let's take this line. This is the vertex. This is a vertex, and all the points on the diagonal are inside the polygon. So this is a diagonal, and this is not, because the whole here the whole line is outside the polygon. You can draw this. Here this part is outside, so this is also not a diagonal. So generally a diagonal is, joining a line joining two vertices of the polygon such that the whole diagonal should be inside the polygon. So this is an example of a correct diagonal. This is not a diagonal. This is not a diagonal. Again, yeah, this is a diagonal. Yeah, this is not a diagonal. So yeah, you guys get it, right? These are diagonals and these are not. So joining any two vertices won't give you a diagonal unless it's a convex polygon, because if you take a convex polygon, something like this, okay, sorry, I don't know, something like this, joining any two because it's a convex polygon, if you join any two vertices, the whole diagonal will be inside. So the whole line will be inside. So every line joining two vertices will be a diagonal in convex polygon. In general, it won't be. As you can see, this is an example. Fine. So yeah, triangulation is you divide a polygon into triangles by drawing diagonals. Okay. Another thing, a simple polygon is a polygon which does not intersect itself or doesn't have any holes. Okay, so what is a hole? Let's say this is a polygon, and yeah, so this is an example of a polygon with holes, something like this. You generally don't need to concern yourself with this. So yeah, I just wanted to tell you that this is an example of a polygon with hole. Okay, with hole. And we'll be discussing about triangulation of simple polygons, which means they don't intersect themselves and they don't have holes. Okay, so let's take this polygon. Actually, all these slides are from my class. I am actually in that course, and I took the slides from the course itself. So yeah, so this is a simple polygon because there are no holes and it doesn't intersect itself. And this is not a convex polygon because clearly, let's say some angle is greater than 180. This angle is greater than 180. And an example, this is not a diagonal again. Fine. So what we'll be doing is, just a minute. So triangulation is keep on adding diagonals so that P is partitioned into triangles. And again, in a triangulation, no crossing diagonals are allowed. Vertices of all triangles must be the vertices of the polygon. So yeah, clearly see this is the triangulation of the polygon because every region is a triangle. So this is all of these regions are triangles, and all the vertices of every triangle should be the vertices of the polygon. So let me draw something like this. Okay, let's say ignore these pink ones here. Okay. Here too, like this is a triangle, this is a triangle, this is a triangle, and this is a triangle. And this won't be considered a triangulation because this vertex is not a vertex of the polygon, right? So yeah, all the vertices of a triangulation should be the vertices of the polygon. So this is the polygon with 11 vertices, and we drew 8 diagonals, and the number of triangles is 9. So let us count 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 triangles and there are 8 diagonals. So do you guys so what do you guys think? Let's say for a polygon, do you think there exists a unique triangulation, or do you think there are multiple triangulations possible? What do you guys think?
There should be multiple.
Yeah, there should be multiple possible. So, and what about the number of triangles for a specific polygon? We just said that there are multiple triangulations possible. So do all the triangulations have the same number of triangles, or do they have different number of triangles?
Same.
Yeah, same. It is pretty easy to see too. We'll be seeing that later. Triangulation, a partition of P into triangles by a maximal set of non-crossing diagonals. It is a maximal set because okay, can somebody vaguely convince me why this is a maximal set of diagonals you can draw without crossing each other? So like if I draw some other diagonal, in this case something like this, it crosses with a diagonal you already drew. So can somebody convince me why if you draw any other diagonal, it will cross at least one other previously drawn diagonal? Does anybody want to give it a shot? Like an intuition as to why that happens, why it is a maximal set.
Like our algorithm is keep on triangulating until we are done. So if we don't stop, so we have to stop at some point.
Okay, why do you think we have to stop at some point? Why can't I? Okay, all right, okay, fine. Okay, and what I had in mind was because each region was a triangle. So if there are no diagonals in a specific like each region is a triangle. Now, okay, let's say there is a diagonal, something which doesn't intersect. Okay, let's say, okay, there is a diagonal which you can add, which doesn't intersect any other diagonal. So that diagonal actually joins 2 points. And okay, Yeah, I guess what you said was correct. I mean, if they are in the same triangle, if they are in the same triangle in the triangulation, then that is not possible because triangles don't have any diagonals. And if they are in different parts, then I guess we
Then
have
they
to
will
prove something else.
cross
Yeah,
one
we have to
edge.
prove why it crosses some other edge. Yeah, I guess it's not that easy. Okay, fine. Yeah. Yeah, so somebody previously said that there are multiple triangulations possible. This is one example. This is one triangulation and this is another one. So the same polygon, there are two triangulations for this. Triangulation is not unique. So triangulation is not unique, but the number of triangles and the number of diagonals is the same for all cases. Okay. So now let's look at this theorem. A simple polygon P can always n is greater than or equal to 4, obviously, because for a triangle, what do you mean by triangulation? Can always be triangulated using exactly n minus 3 diagonals that partition P of n into n minus 2 triangles. So anybody of you want to take a shot at the proof, or at least tell me how we can proceed for this? Like any specific technique to prove this? You guys can take 2 minutes if you want. You guys can try it. I'll just give 2 to 3 minutes, I guess. If you have an idea, or if you get the proof, or very basic intuition of how to proceed with it, you can speak up.
I think it is easy to see in convex polygon, but in
Convex
every
polygon, it's actually very easy, right?
yeah. But in means in general polygon, how to proceed? It is little difficult to think.
Yeah, I mean, like, do you have any vague idea as to any direction we can proceed in? Specific proof technique or something?
Like we can break it into, I mean, smaller regions of convex portions and then add them.
Convex portions.
Yeah, I mean, we can partition it into small convex regions and then apply on these and then add them.
I mean, I think there are some polygons such that the smallest convex, I mean, like if you want to partition a polygon into smallest, into convex portions, I think there are some polygons such that all the convex portion should be a triangle, something like that. Like there is no other convex portion larger than a triangle. I mean, you can actually make up such a triangle, such a polygon, I guess. Yeah, so that won't actually work, because to do that we'll need to partition it into triangles to triangulate that. So yeah, so you are in the right direction though. We'll just wait for another minute, I guess. You guys are in the right direction. So you guys are thinking about dividing. So what else comes to mind when you think about dividing something into smaller parts or something? Yeah, fine. Like if you take some polygon, okay, sorry. If you take some polygon like this, like each angle is a reflex angle except the last one, and you want to partition it into convex parts, the only way you can do is, I guess, something like this and then something like this, I guess. Yeah, so the only way you can partition it into convex parts may be the triangulation for some polygon. Yeah, so that won't work actually. So yeah, okay, let's do this. It's actually, you'll probably be surprised because it's not. Yeah, go on.
Like we can just take the sum of internal angles and divide it by the sum of an angle of the triangle, like 180 degrees.
Okay, then.
Because
Okay, then you will probably know that. Okay, yeah, that will. Okay, let me see. Polygon can always be triangulated using exactly n-3 diagonals.
for the
So, yeah,
triangles, I'm saying.
Yeah, that should work. Okay, another thing, yeah, that should work. What you said should work, I guess. Another thing, you guys actually went in the right direction. You said divide. You said divide. You basically had something like divide and conquer. You divide the polygon into parts and conquer. What the another way is induction, because yeah, assume it holds for some k less than n, and let's say, I mean, okay, another one thing we need to assume I guess, assume is that each polygon has, okay, wait. Yeah, okay, sorry. What you guys said is correct. Okay, fine. It is basically induction and divide and conquer kind of thing. Another thing we need to have is that we need to assume that there exists at least one diagonal in a polygon. So that thing I don't know how to prove, I guess. I mean, it won't be that difficult to prove that there is at least one diagonal in a polygon. Yeah, that thing, yeah, I don't know. I should actually look at that. So the proof goes like this: you draw a diagonal, and that will basically split your polygon into two parts. Now, for induction, you don't need to actually have convex polygons or anything. You are proceeding by induction. So the base case is quadrilateral. For n equal to 4, you can draw any diagonal and divide it into two triangles. So that is the base case. Now you draw a diagonal. Now let's say there are n1 points on this side and n2 points on this side. Another thing is n1. What is n1 plus n2? So you guys, someone answer this. It's actually pretty simple. If you divide the polygon into two parts, and let's say this polygon has n1, this polygon has n2, what is n1 plus n2?
N plus 2.
Yeah, you're counting those 2 points twice. So fine. Now by induction hypothesis, there are n1 minus 3 diagonals here, n1 minus 3, n2 minus 3 diagonals here, and you have another diagonal in the triangulation. So I mean, like, you triangulate this part separately, now you have a triangulation for the whole polygon, right? So total number of diagonals in the complete polygon should be n1 minus 3 plus n2 minus 3 because of induction hypothesis, because n1 and n2 are obviously at least, okay, n2 should be at least 4. Can this be 3? N2, can this be 3? Something like yeah, I guess. Yeah, I mean, it can be 3, I guess, at least. So even if it is 3, n1 and n2 both are less than n anyways. So we know this. So yeah, so the induction from the induction hypothesis, we know that the number of diagonals in each of the parts is n1 minus 3 and n2 minus 3. You add them up, and you have the total number of diagonals in the final polygon should be n1 plus n2 minus 5. And we also know that n1 plus n2 is n plus 2. So the whole thing is n1 n minus 3. Now the same thing for triangles, because there are n minus 2 triangles here, n minus 2 triangles here. And this diagonal actually doesn't add any triangles, because let's say the triangle is something like this, and there is another triangle like this. So yeah, this just splitting it won't add any triangles. So it should be the number of triangles here, number of triangles here. You add them up, you'll have n1 plus n2 minus 4, which should be n minus 2. So yeah, this is a kind of proof. Yeah, you guys were very close, I guess. This is not valid for triangles for polygons with holes. So this is a polygon. I told you before, like a polygon with hole is something like this. For a polygon with hole, you consider all of these to be vertices, like the blue ones and the red ones to be vertices. So you can triangulate it with in some way like this, I guess. Let's try. Yeah, you can triangulate it some way like this. And you can check whether this formula holds for that or not. It probably won't. So there are 8 vertices. You'll need how many? 6 triangles. So you have 1, 2, 3, 4, 5, 6, 7, 8. So yeah. Oh wait, 1, 2, 3, 4, 5, 6, 7. Yeah, 8. Okay, yeah, there are more triangles. So this won't hold for triangles with holes, polygons with holes. Yeah. So we know what a triangulation is and how many triangles a specific polygons can be split into. That is constant, which is n-2. So let's look at the application of triangulation. I won't be telling you how to compute the triangulation of a polygon because it's not as simple as computing the convex hull. But you guys can actually think about it. But it won't be that easy anyways. So if you are interested, you can actually look it up and you guys will be able to understand it pretty easily, I guess. Let me just write it in the chat. You can Google ear clipping algorithm. This is one of the simpler algorithms to compute the triangulation. Okay, so now we'll be looking at an application of triangulation. You might actually think, how is triangulation going to be useful? Like you are just dividing it into triangles. So it's not that obvious to see how it is useful. So, and even the example now I am going to give is also actually not that obvious to see. It is actually a very clever application of triangulation to prove to actually generate a specific thing. Okay, so do you guys know what these pictures are, where these pictures are from? Hmm? Okay, well, these are from Louvre Museum, Paris. I don't know how to pronounce it. Okay, let's call it Louvre, whatever. Fine. Museum, Paris. It is in Paris. The problem with this is its structure is very, very weird. Some architect designed this in such a manner. So the issue we'll be dealing with today is, since this is a very famous museum, it's a very famous museum. I think even the Mona Lisa picture is there. So yeah, so there will be a lot of presentations there, and you will need to keep them safe. You need to watch them, like you need to have some guards inside the museum so that nobody messes with the paintings, nobody steals them, nobody damages them or something. So the issue we'll be dealing with is, let's say this is the shape of the the museum, and now the paintings are on the walls. These are the walls, and there is one painting here, there is one painting here, there is one painting here, there are some painting there is. Okay, so all the paintings are on the walls now. Okay, okay. So let's say, given the floor plan of a weirdly shaped art gallery having n straight sides, so n walls, how many guards will have to be posted in the worst case so that the entire wall is visible to them? So what is the idea? The idea you come up with is, you will put some guards and you will put them at the vertices, okay, so that you will be able to monitor all. You each guard, I mean, like every wall is watched by at least one guard. Let's take this wall. Now this wall is watched by this person. Even this wall will also be, this person will also be able to see this wall. And this whole wall will be visible to this person, and this whole region is also visible to this person, the same person. So I think it's not that difficult to see. These 4 guards should suffice for this specific, floor plan. So you would like to know, for a random shape with some n, let's say n walls, how many guards should I hire so that the whole wall is visible to them, and where should I place my guards? You get the question? Is it Is it?
Yes.
Yes. Yes.
So do you guys have any rough estimate as to how many? Let's say there are n. Do you guys want to take a guess? Let's say how many are the minimum, maximum? Okay, let's say how many number of guards do you think we will need to monitor all the balls? Let's say in worst case, and you want to place them optimally. So how many number of guards do you think? And I mean, like, I don't expect you guys to make an educated guess or something. So just intuitively, how many do you think? Hmm? Well, I mean, if you don't want to guess either, fine, I guess. Yeah, okay, fine, go on.
Maybe half or
Yeah, it's around that thing. Okay, so actually, this is the question posed by. This is actually a problem called art gallery problem. It's actually quite famous. If you Google it, you'll get tons of articles on it, I guess. So this is a famous problem called art gallery problem. The problem is here, the problem statement. You guys understood this. Now, this problem was originally posed by Victor Klee to Vasek Schwartal, I guess. Okay, so he posed it in 1973 and he solved it in 1975. The answer was step of n by 3. So there are some, okay, so what is n by 3? So let me say, there are some floor plans such that you'll require at least this many number of guards. Okay, so there exist some polygons such that you will require these many number of guards, and for any polygon, these many number of guards should suffice. That was what he proved, and the proof was correct, but the proof was very complex. I guess it took something like 3 to 4 pages, very complex math and stuff. So yeah, this is what he did. It was actually a very good result. So what he was able to prove that for simple polygons, n by 3 guards is necessary and sufficient to guard the gallery when there are n vertices in the polygon. So we said n sides means n vertices. So yeah, step of n by 3 is sufficient. Is sufficient means you can take any polygon, and if you hire n by 3 guards, you should be pretty good. I mean, like, you don't need to hire it anymore. And there are some polygons such that you will need n by 3 number of guards. If you guys want an example or something, it should be something like this comb type of polygons. I mean, like, I won't be going into this. So yeah. So if you guys want to think about this, you guys can think like, okay, let me just see how many sites are there. So 2, 1, 2, 4, 6, 8, 10, 12, 13 sites are there. And how many guards do you think we'll be needing? So, okay. So for each of these things, you'll be needing one at least. Okay, wait, probably here, I guess. I actually don't remember. I think you'll be putting them somewhere here so that they are able to see everything, I guess. I'm not sure. Yeah. So for some example like this, some similar example like this, you'll be needing exactly n by 3 number of guards. So yeah. And he also proved that there are at most, I mean, like, you'll need at most n by 3 for any such polygon. Like if you take some random polygon, something like this, you will need at most n by 3. That's what he proved. However, this proof was very complex and used the method of induction. Yeah. So he proved this in 1975. He proved this in 1975. In 1978, Steve Fisk constructed a much simpler proof. Actually, how simple this proof is, like, you can actually write this whole proof in something like 2 or 3 lines. You guys probably need to know coloring of a graph or such. It's actually very simple. If you want, I won't be discussing that. So if you want, you can actually have a resource here. I'll be sharing the slides anyway. So if you are interested, you can look through this, which is a method of decomposing a polygon into triangle. So he used triangulation to solve this problem in 2 to 3 lines, whereas this guy actually took some 2 to 3 pages and very complex proof by using induction. So yeah, there are some very clever applications of triangulation like this. Yeah, so he decomposed the polygon into triangles and colored the vertices. So yeah, if you're interested in the proof, understanding it doesn't have any prerequisites. I guess you'll need, yeah, it actually doesn't have any prerequisites. So you can actually look at this PDF. I'll be sharing the slides, so you can download this PDF and read. It's actually, yeah, it's quite simple. You'll be surprised as to how intuitive how easy that proof is. Yeah. So that's all for today. If you guys have any other question or feedback, or you have anything you guys want to add, go on. Otherwise, we can exit now. I'll share the slides. I'll put it in, I don't know, reading materials, I guess. Yeah. So do you guys have anything to add? All right, I guess. I'll see you later. Bye then.
Thank you.